Let's look into the fundamental theorem of calculus a little bit more. We have already talked about what is officially dubbed part 2. It's your evaluation theorem, where if you want to find the area under a curve or evaluate a definite integral, then you find the antiderivative, plug in upper limit, lower limit, subtract the 2. And that is part of the fundamental theorem of calculus. There is, however, a second part which deals with integral defined functions and finding the derivatives of those functions. So I have an example right here. G of x is the antiderivative from 2 to x of t squared plus 1, and I want you to find g prime of x. So there is a differentiation process for this, but at the moment, we don't know what the process is for the derivative of an integral defined function. So what we're going to do for this time only is I'm going to start by finding g of x first. Let's try find. There we go. We're going to find g of x first, and we will simply find g of x by doing the antiderivative and evaluating. So if g of x is this integral, I'm going to start by ignoring those limits of integration. And the antiderivative of t squared plus 1 would be t cubed over 3 plus t. But this was a definite integral, so now I need to evaluate that from 2 to x. And so I will plug in the upper limit, x cubed over 3 plus x. I will plug in the lower limit. 2 cubed is 8 over 3 plus 2. And that is an expression for g of x. So all I did to get g of x is I computed the antiderivative and evaluated it based on the limits of integration in the antiderivative. If you want to, we could simplify 8 thirds plus 2. That ends up being 14 thirds. So my function g, it can clean up to x cubed over 3 plus x minus, and double checking that is 14 thirds. Okay, so I just went through that process and I found the function g, but the question was not for g, the question was for g prime. So now that I've done that, I have turned g into a much more familiar function. It is just a polynomial, and I know how to differentiate a polynomial. To differentiate a polynomial, I use the power rule, and the derivative of x cubed over 3 would be 3x squared over 3. Leave the 3 on bottom and differentiate the top. The derivative of x is 1. 14 thirds is a constant, so I don't care, or that's going to zero out when you differentiate it. And that would, the 3's cancel, that does reduce to x squared plus 1. And if you look at your final answer, that might look familiar, and it should, because what we did is we found the antiderivative, then we did the derivative of the antiderivative, and as you should have expected if you were thinking ahead, I ended up with the same thing, essentially, that I started with. I started with t squared plus 1, I ended with x squared plus 1, and the variable changed because there was an evaluation step where the x's replaced the t's, and that's not coincidence. When you do the derivative of an antiderivative, you kind of go in a circle, you get what you started with. So that is part 1 of the fundamental theorem of calculus. If you have an integral defined function, and you want the derivative of that integral defined function, it's really easy. The little process for it is extremely easy. All you do is you take the upper limit of x, and it replaces the t, and you're left with f of x instead of f of t. Now, one thing you do want to check for, you want to make sure that you are going from a constant. You need to make sure that your bottom limit, your lower limit, is a constant, because if it's not, we will have to address that. But as long as that lower limit is a constant and you're going from constant to x, then your derivative is quite easy. So let's do a couple of examples of this. I have 4 right here. So if g of x is the antiderivative from pi to x of sine t, and I want g prime, this is going to be painfully easy. Pi is a constant. I'm just going to take the x and plug it in for the t. G prime is sine x. That's your derivative. That is it. Number 2, 5 to x. Guess what? G prime, we're just going to plug the x in for the t. Natural log of x squared plus 1. Number 3, I'm going to change number 3 ever so slightly. I want to put a second t in here. I'm going to make that t cubed plus 5t. And if you notice number 3, this one, it's not variable to constant to variable. my variable here is in the bottom. So before I try to apply part 1 of the fundamental theorem, I'm going to rewrite this. I really want that 7 to be in the bottom instead of on top. So I'm going to do that. However, if you flip the limits of integration, it makes the antiderivative negative, or it returns the opposite result, however you want to think of that. So I copy everything else down. Now I can actually use that little formula, a little process where I plug the x in for the t. And if there are multiple t's, this is why I wanted to change this one. If there are multiple t's, then the x replaces all of them. So the negative outside comes along for the ride. And when I plug in x, I get x cubed plus 5x. And there's your derivative for number 3. And then number 4, I've uglied it up a little bit. It is from constant to variable. And you may be guessing, well, wouldn't we just plug in? Wouldn't we plug in that variable, that expression, x squared plus 1? Doesn't that replace the t? And yes, it does. We will substitute x squared plus 1 for the t. However, the fact that this is uglier than just an x introduces a new situation that we need to talk about. So before I do the answer for number 4, let's talk about what to do when you have constant to some function rather than just an x. So what we're going to do here is I'm going to decide, I'm just going to make the proclamation that capital F of x is the antiderivative. Capital F is the antiderivative of little f. So if I make that proclamation, then this definite integral right here ultimately turns into the antiderivative of little f, which is capital F of t. And I'll evaluate that from a to h. And that would be my function g. I'm going to continue on. I'm evaluating the definite integral. I have a generic antiderivative. I now need to plug h of x in for the t. So g of x is going to be capital F of h of x minus capital F of a. So I have an expression for g by evaluating the definite integral. Now, if I want g prime of x, I need to differentiate this guy. And if you look here, this becomes a chain rule. This is f of h of x. It's not just f of x anymore. There's something uglier in there. So we have to chain that. And the derivative of f of h of x would be f prime, leave the h of x alone, times the derivative of the h on the inside. Wow, my writing is shaky today. Times the derivative of the h on the inside. And f of a, capital F of a, because a is a constant, then f of a would be a constant as well. So the derivative of that would zero out. And this is the derivative of g. And so you always need to remember that if you have an uglier function on the inside, you still substitute it in for the t like you did if it were just an x. However, you do need to remember that it's a chain rule. And so we have to multiply by the derivative of what's substituted in for the t. So let's go back and revisit that number 4 we looked at a minute ago. I'm going to take the x squared plus 1. That x squared plus 1 will replace the t in my integrand. And g prime of x ends up being the sine of the square root of x squared plus 1. But then you always multiply by the derivative of what replaced the t. So I plugged in an x squared plus 1. The derivative of that is 2x. And there's your derivative. So it's just one extra little tiny step, but it's one that people very, very frequently forget. You always multiply by the derivative of what replaced the t. And I would even encourage you to do that when the derivative is just 1. So like if I followed that rule of completion on these first 3 problems, I substituted an x for the t. We will then multiply by the derivative of what replaced the t. But if it's just an x, then you're multiplying by 1. So in these cases, it's not mandatory, but it still is a good idea to remember to multiply by the derivative of what replaced the t. And so I would recommend you put times 1 on every one of them, because if you do this all the time, then you won't forget it when it's actually necessary on problems like number 4. So let's look at number 5. 5, we have that problem again where the constant is in the wrong location. So I'm going to flip the integral, make that negative 12 to sine x of t over t cubed minus 5 dt. And if that is my g function, then g prime, I'm going to take that sine x. It replaces both t's. So it's going to be the sine of t over the sine cubed of t. But then we need to multiply that by the derivative of what replaced the t's. The derivative of sine x is cosine x. Ooh, and I made a mistake. It should be sine x replacing the t's, not sine t. So let me erase those t's and replace them with x's. Whoops. Sine x, sine x. There we go. And that would be the correct derivative for number 5. And then one more situation, and I'm not going to go into details about the proof of this, but if you have a variable to variable, there's no constant here, we do have the option. I'll show you very quickly what the mathy way of doing this is, but you really want constants in here, so what you could do is split this integral using one of the properties of antiderivatives, and I could change this from x to any constant of the square root of the natural log of t squared plus the antiderivative from constant to x cubed of the square root of the natural log of t squared dt. You could split the integral into 2 using the addition of integrals property. And then we now have 2 problems where we have constants involved. We would need to flip this one, make it c to x, so my constant's on bottom. However, the little process, the memorized process for this that we will use for the derivative, while that is a longer way of working it out, I'm going to just kind of put that on hold, just keep it in thought cloud land over there. When we do the derivative and there are constants on both bottom and top, then we do it almost like we're evaluating an antiderivative, only we're kind of mixing the antiderivative process, the evaluation process, with the part 1, the differentiation process. I'm going to start by plugging in the upper limit. I'm going to plug in x cubed for the t. And so that's going to be the square root of the natural log of x cubed squared. But I plugged in the x cubed, so I then need to multiply by the derivative of what replaced the t. So I'm going to multiply by 3x squared. And then I'm going to plug in the bottom one. I'm going to plug in the x and repeat the process, and we will subtract the 2 things. So I plug in the top one minus, plug in the bottom one, square root of natural log of, I'm plugging x in for the t. And just to kill this thing dead, I'm going to multiply by 1 because that is the derivative of what replaced the t's. And there is an explanation of part 1 of the fundamental theorem of calculus.